So welcome to this class. This is about ionization energy. So the learning outcome of today's class is first to understand what's meant by ionization energy, and second, also to understand factors affecting the ionization energy, uh, such as the nuclear charge, distance from the nucleus, and shielding. Okay, so to start with, let's define the atomic radius. So atomic radius is basically the half distance between two adjacent nuclei. So if you have two nuclei of the same atom, the half distance between the two of them is regarded to be the nucleus or the atomic radius. Okay, so what are the factors that are affecting the atomic radius? Fine. So you may ask, okay, so what is the relationship between the atomic radius and ionization energy? Okay, so instead of going any further, let me just give you an idea. Ionization energy is the energy required to remove the electron in the outermost shell. Okay, so let me draw this to you. Okay, so here if we have the nucleus, and here we have first shell, second shell, third shell, and here we have 3 electrons. So this shell here is called outermost shell. Outermost shell. That means it is very out, or it's the valence shell, if you like. Outermost shell, and sometimes also we call it valence shell. Fine. Now, here we have electrons. This is the nucleus. And here we have electrons. These electrons and these electrons, you call them core electrons. Core electrons. And these core electrons are found in the core shells, the inner shells. And the electrons that are found on the surface, if you like, you call them outermost shell electrons or valence electrons. Fine. And these are the ones that are exposed to the external space, if you like. And these are the ones are involved in the chemical bonding and chemical reactions. So basically, we are studying the atomic radius because the atomic radius, it will heavily affect how these electrons are attached to the nucleus. If these electrons, the outermost shell electrons, are very much attached to the nucleus, it will be very difficult, or it will take so much energy to get rid of them or to remove them from the outermost shell. But if these electrons are far away from the nucleus, then you require less energy to remove them. So the ionization energy, again, is the energy required to remove electron from the outermost shell. We will take more specific definition as we go on, but for now, let's understand it this way. The amount of energy required to remove this electron, the outermost shell electron, not the core electron. We don't deal with the core electron here. We're dealing with the valence electron or the outermost shell electron. Okay, so just to erase this. Fine. So we want to see what is affecting the atomic radius. Atomic radius, basically, if we go across the periodic table, atomic radius, it basically increases as we go down the group, and it decreases as we move across the period. So this is the period, and this is group. So as you go down the group, what will happen? More shells will be added. Why more shells will be added? Because you need to add more electrons. So as you need to add more electrons, you need to add more shells, and therefore basically the atomic radius will increase. So let's demonstrate that. Okay, so here, basically, you have maybe few electrons, 3 electrons, and then you add more shells to fit in the extra electrons of the next element, and then you add more shells to add more electrons, and here you add more shells to add the extra electrons. So as you can see here, the distance between the nucleus and the outermost shell electron, the nucleus and outermost shell electrons, the nucleus and outermost shell electrons, nucleus and outermost shell electrons is increasing. And as it is increasing, the attraction between this electron and the positive charge decrease. Now, on the other hand, when you go across the period, what will happen? The atomic radius, it will decrease. Okay, so somebody may ask, okay, but we are adding electrons as we go across the period. So what happens? Okay, so as you go across the period, you are adding electrons, but you are adding them to the same shell. Fine. And because the number of proton also is increased, so there are here two forces. You are adding more electrons. That's correct. And these type of electrons, they will cause some repulsion amongst themselves, but also you are adding more protons. So the force of attraction between these electrons and the nucleus, which is the protons that you have added as you went across the period, is greater than the repulsion between the electrons, and that's why the atom is getting sort of smaller and smaller. So here the positive charge is increasing as you go along. Okay, and as the positive charge increases, it attracts the electrons at the outside, or valence electrons, and therefore basically the atom shrinks, if you like, gets smaller. Fine. So these are the two factors that are affecting the atomic radius. As we go across the period, what will happen? As we go across the period, the atomic radius, it decreases. As we go down the group, the atomic radius increases. It decreases here because of the increase of the nuclear charge, and it increases here because of, sorry, it decreases here, because I said increase, it decreases here because of the increase of the nuclear charge, the number of protons as you go from this element to this element to this element. And here the atomic radius, it increases here because you are adding extra shells to fit the extra electrons in. Fine. So you will find this explanation here. Okay, so what is ionization energy? Ionization energy, firstly, I would advise you to look at this video, but let's move on and see the definition of it. The ionization energy, just let me get the definition. Yeah. The ionization energy, or let's be more specific, the first ionization energy of the element or an element is the energy needed to remove 1 mole of electrons from each atom, and 1 electron from each atom in mole of atoms of the elements in gaseous state to form 1 mole of gaseous state ions. So here you have 1 mole of gaseous atoms. You need basically to remove 1 mole of electrons from them, because now you are mature students. Previously, at an early sort of stage of your study, you used to call this electron, or to read this electron, to read this equation as follows. You used to say, I have 1 atom, and this atom is in the gaseous state, and this atom basically, it's converted to 1 ion, positive ion, and 1 electron. Okay, now let's agree to this. In chemistry, when you read the equation, there is nothing such as 1 atom or 1 molecule. Always it is 1 mole. 1 mole of X atoms. X here means any atom. It basically converted to 1 mole of X plus, 1 mole of ions. Why is that? Because they have lost 1 mole of electrons. So what is the mole? Mole is basically a quantity, and this quantity is quantified as 6.023 times 10 to the power 23. So if you are talking about an element in the gaseous state, so it is 1 mole of element in the gaseous state. If you are talking about a positive ion, so it is 1 mole of positive ion, which is this number. And if you're talking about 1 mole of electrons, so it will be this number of electrons, okay? So it's the energy required to convert 1 mole of atoms in the gaseous state to 1 mole of ions in the gaseous state, plus the 1 mole of electrons that's been lost, okay? So this is basically the ionization energy. First ionization energy of an element is the energy needed to remove 1 electron from each atom in 1 mole of atoms of the elements in gaseous state to form what? To form 1 mole of gaseous ions as a +1, okay? And the reason we call that first ionization energy, because we have removed 1 electron only. So imagine with me that this is your atom. So here you have the nucleus, the protons here, and here you have electrons, and here you have 3 electrons, and we call these outermost shell electrons or valence electrons. So the first time, if you remove this electron, you call it, and maybe the value, let's say 1,000. Value of this energy needed, 1,000 kilojoules per mole. That means you need 1,000 kilojoules to remove 1 mole of these electrons. So if you remove this electron, the first electron that I'm pointing at, you require this. So this is, we call it first ionization energy. Now, you have formed this, fine. Now this one, you want to remove further electron from it, another electron from this species here. So if you remove this electron, you call it, and maybe the value of energy needed is 2,000 kilojoules per mole. So you call this ionization energy second ionization energy. And if you remove this, you call it third ionization energy, etc. Okay? Okay. So understood what's meant by the ionization energy. There is another concept that we need to understand, because this concept is basically affecting the ionization energy, and this is called shielding. Electron, so I'm reading here, the electron in lower energy level shields electrons in higher energy level from full attractive force of the nucleus. Electrons in the same energy level do not shield each other at similar level. So let's see what happens here. Okay, now we have a nucleus, and here we have electrons, 1, 2, 3, 4, 5, 6, 7, 8, and here we have 2. And here, this is our nucleus, and has maybe 8 or 10 positive charges, protons. So this is 10. So these here, these electrons in the just adjacent to the nucleus, they enjoy the positive charge so much. Imagine that it's a group of students here, and they are around the fire, and they are enjoying the heat. So these group of students are enjoying the heat in full. But these 2 students who are sitting at the back, they are being shielded by means of these students. They don't have the full experience as these ones. So these ones are experiencing more heat than these ones. Similarly, if you look at the electrons, so these electrons here are experiencing the 10 positive charges or 10 protons, the nuclear charge in full, but at the same time, they are shielding some of this positive charge to reach to the other electrons. And that's why this is called shielding effect. So these two electrons at the back, they will not be experiencing, they will not feel the positive charge as these electrons see it. And therefore, basically, this will affect the ionization energy because they will not be as attracted to the nucleus as these 8 electrons. Is that clear? So the shielding effect is basically, it's when the electrons, the core electrons, they will shield some of the nuclear charge to reach to the valence electrons, and therefore, basically, the valence electrons will not see the full positive charge as the other electrons do. And since the valence electrons will not feel the positive charge, then it will be easier to remove them because they will not be as much attracted to the nucleus as the core electrons. Okay. Okay, effective nuclear charge is basically how much the valence electrons feel or see from the nuclear charge. So let me draw this again. So here we have the proton, or we can call it a nuclear charge or positive charge. And here we have 8 electrons. And here we have, let's say, 1 electron. Now, here you have these 8 electrons, they are experiencing the full of the nuclear charge. So the nuclear charge is so effective for these 8 electrons. But this 1 electron, it doesn't see 8 because some of it is being shielded by the 8, as we said. So it sees less than 8. It sees, this electron sees less than 8 of the positive charge. Okay, so if the value here is 8, so this 8 electron, or this outermost shell electron, it doesn't see the full 8 or 9 positive charges. Is that okay? So that's why we have this new terminology, effective nuclear charge. So what's effective nuclear charge? Effective nuclear charge means how much the outermost shell electron sees or feels from the nuclear charge after you take away the shielding effect. So the Z effective is the nuclear charge minus the core electrons, okay, which is basically the shielding effect. Fine. You don't need to quantify it, but just it's important to understand this terminology. So far we have learned about shielding, and this is called by the core electrons between the nucleus and the outermost shell electrons or the valence electrons. These electrons in between, they shield the nuclear charge. They don't let the nuclear charge or the charge of the proton to reach to the electron in the valence shell. And therefore, it becomes easier to remove these electrons from the valence shell. The effective nuclear charge is how much the outermost shell electron feels from the nuclear charge after you subtract or after you take away the effect or the shielding effect. Okay, the next thing here, let me just yeah. Okay, the next thing here is the ionization energy which went through, and then the factors affecting the ionization energy. First factor here is the size of the nuclear charge. So as the nuclear charge is bigger, you have lots of protons, it becomes more and more difficult to remove the outermost shell electron. Second thing is the distance of the outer electrons from the nucleus. So as the distance between the nucleus and the outermost shell electron gets bigger and bigger, it becomes easier to remove the electron because the attraction is less. And the shielding effect of the inner electrons. As the shielding effects, as you have more and more electrons between the nucleus and the valence electrons, as it's becoming easier to remove the electrons in the outermost shell or the valence shells because of the shielding effect. Okay. In the next part of this video, we will be looking at the successive ionization energy, and then we also will be looking at some sort of applications to the ionization energy on periods. Hope that was beneficial, and I'll see you in the next part of this video.